Hi, gang. Today we're going to talk about Bernoulli's principle. Bernoulli's principle deals with the flow of fluids and how there are energy differences with the flow of fluids, and that ultimately leads to an understanding of how pressure changes as fluids are flowing. We are going to assume we have ideal fluids. On the screen, you can see some of the properties of ideal fluids. They're non-viscous, they're incompressible, their motion is steady, and they move without turbulence. This is not how the real world works, but changing one of these to being a dynamic value, for example, the fluid is accelerating and the fluid speeding up and slowing down, creates a wide variety of mathematical challenges that require calculus and math that we do not need at this time. We're going to start off with the continuity principle. This is a very important equation when it comes to an understanding of Bernoulli and the flow of fluids. We can see on the screen a pipe. That pipe has two different cross-sectional areas. It also has an elevational difference in this particular picture. And so what we want to talk about right now is the idea that as a fluid flows through a channel or a pipe without an elevational difference, just that concept where, for example, we would have imagine a channel of water. The channel of water that we're looking down on. As that channel of water we're looking down on flows, all of a sudden there's a restriction at some point, and then it widens back out. And what happens to the velocity of that water as it's moving through that channel? Since the fluids in the pipe have to move with a consistency, and that the mass at two different points in the pipe has to remain the same. That is, that for the water back here to flow through this region, the water that was in this region has to move out of the way. What that means for us is that when we restrict the pipe, that we end up seeing that the water comes out with a greater velocity. So to keep the same mass, if this cross-sectional area horizontally, just assume this horizontal cross-sectional area that slices through the pipe has the same width as the part I marked here, there is more water flowing through the right. There's no more water flowing through the right section as in the left section at any given point in time. Since over on the right we had that restricted area, that means that we have to have a faster moving water to get the same amount of water through, same mass of water through. So with that understanding of this equation here, or this concept here, that allows us to derive the equation to describe what it is that we are saying here. And so what we find is that the mass is equal to the density divided by the volume, or mass is equal to, right here, mass is equal to density times volume. That means if we said that the mass that flows through here and the mass that flows through here is the same at any given point, that the density times the volume, which is mass, is going to be the same. So rho V1, this is volume, is equal to rho V2, which is also volume. Since the fluid is ideal, the densities are the same. We're not seeing a change in density. And so this simplifies down. Rho 1 and rho 2 would cancel each other out. And so this simplifies itself down to volume 1 has to equal volume 2. Since volume is equal to cross-sectional area times cross-sectional area, meaning the slice of the pipe, times the slice of the pipe, and when we have a pipe that runs, for example, like this, we're just talking about the slice times x, that's volume. So we can rewrite the volume equation like this. We know that X is equal to velocity times time. This is an old equation. The little v here stands for velocity. The big V stands for volume. And so we can substitute that in for X, and we get the next line of equation, which says that the area is equal to the velocity times time. Remember, velocity times time is X. Area times X is equal to volume, and that gets us back up to this original idea. Since the time is the same, things have to happen sequentially. T1 is equal to T2. That cancels out, and therefore we get this nice equation at the bottom, which we call the continuity principle. The continuity principle says that as the cross-sectional area of a pipe changes, the velocity changes inversely. So as A goes down, cross-sectional area of this pipe would be the area that's slicing through the screen. As the cross-sectional area goes down, then the velocity has to go up. It speeds up in that area, which is what we originally said in this portion of the presentation. That concept of, and this slide just sort of repeats what I've said here, that concept of AV, area times velocity, is what we call the flow rate. And so we say that the flow rate in this pipe must remain constant. The velocity may change, the area may change, but the flow rate must remain constant. And ultimately, if the velocity changes, the area had to change. As the velocity increases, this is a very important statement. One of the most important statements I'm going to give you this year. As the velocity increases, then the pressure decreases. Pressure is equal to force over area. We've talked about that before. We're going to talk a little bit more about that. Velocity increases, pressure decreases as we move along. Again, the equation is the consequences of the equation that we had on the screen is that the mass flowing through any given portion of that pipe in any given period of time is the same. Another way of thinking of that is if I were to slice the pipe out off here and fill a bucket, or if I were to slice the pipe off here where it's a little fatter and fill a bucket, it would fill at the same rate. The same amount of mass of water is coming out in any given second. The difference is that the water down here in this tighter region is flowing faster. Less atoms coming out at any given instant, but in 1 second, the same amount of water is coming out. So it's flowing out faster. It's moving out of the way faster. And so that is the continuity principle. This leads us to the main focus of today, Daniel Bernoulli. There he is, Swiss physicist and mathematician, studied fluid dynamics. For fluids to flow in a pipe, there are two ways that we get fluids to flow in the pipe. We can tip the pipe so one end has a greater potential energy and the water flows down the pipe. So you imagine a glass of water and you tip it on its side, the water starts to move. Or you have a hose and you're holding it perfectly level, and you could imagine there's water sitting in that pipe, and the minute you pick up one end of the pipe with a greater potential than the other, then all of the water flows down. It's sort of like a marble effect. If this is a flat surface right here and I have some marble sitting on there, the minute I lift this up, they start rolling down the incline, right? They start moving down the incline. The other way is to apply a pressure or a force to the end of the pipe to cause that fluid to move. Gain potential energy or gain potential energy, which is free to flow to kinetic energy, or apply a force. Bernoulli's equation is going to make some assumptions. Again, this is for basic understanding, but we're going to assume that the fluid is incompressible, non-viscous, and flows in a non-turbulent, steady manner. This is ideal. We're only going to deal with ideal this year. And so that leads us to Bernoulli's equation, which you can see on the screen, that the pressure in the pipe plus 1/2 rho v squared, where this is the velocity. This is like the kinetic energy. If you think of kinetic energy, it's 1/2 mv squared. We'll get back to this in a moment, but when we look at this equation, we can see that this is going to be all about energy. So 1/2 rho v squared, v is velocity, plus rho gy, this is like potential energy, mgh, is equal to a constant. Usually the way we see it is we see this equation ran twice, so we would say that constant would be P, the pressure, plus 1/2 rho v squared plus rho gy, rho g, then gy. And so we would say that if we gain elevation, then if we gain elevation in y, then these two factors over here had to go down, or at least one of them has to go down. So these are, again, the three equations that describe what's happening in the pipe. We have pressure, kinetic energy, and potential energy. So if we remember, pressure is equal to force over area. And so we are ultimately seeing that the pressure is pushing on this pipe, and pushing on the fluids, causing it to move. So how this comes into play here? So how this comes into play here is going to be, and I'm going to erase what I have on the screen and rewrite this equation to be force over area plus 1/2 the mass divided by the volume, just to keep that's volume. I'm going to put VO there, times the velocity squared plus mass divided by the volume, VO, L, I guess maybe to keep it from initial velocity, volume times gravity times y has to equal, again, what is on the right side is exactly the same thing, force over area plus 1/2 the mass times the volume plus times velocity squared plus the mass times mass over the volume times gravity times y. Same equation on the left and the right. What I want to talk to you, though, about is simplifying this. If I multiply volume through everything, what I get is volume over area. And volume over area is length times width times height, or divided by, let's say, width times height, the area, cross-sectional area. So the width and the height cancel out. I'm left with length. I'm going to change that to the variable x. And so the reason I said that is in this first part was force over area. Then I change this to force times displacement plus 1/2 mv squared plus mgy is equal to force times displacement plus 1/2 mv squared plus mgy. Daniel Bernoulli was smart, but he understood the concept of energy, and he proved that fluids conserve energy. That's really what he discovered here. And we have conservation of energy. The Fx is the work done, external work. This would be a piston pushing it, or a pump pumping it. That's external energy, force times displacement, plus the kinetic energy, plus the potential energy, gravitational potential, is equal to the same thing on the other side. It's just conservation of energy that we've always had. And that's what Daniel Bernoulli found. Some things that we can consider based on this is that as the cross-sectional area is going to change, we are going to see that there is going to be a change in the velocity. Considering that pressure and velocity are restricted in the pipe, and there's no change in height, force, or density, cross-sectional area is going to, as the cross-sectional area goes down, the velocity goes up. That has to happen in the equation. Think about it. If we keep no change in height, then the potential energy has not changed. So that the mgy component is not changing. That leaves only two components in this equation. Those are the pressure and the kinetic energy. And so if we are seeing a change in the cross-sectional area, that's a change in the pressure. If there's a change in the pressure, then the velocity has to change inversely. So as the area goes up on one side of the equation, then the velocity has to change to keep it constant, to keep this value constant. And so this reinforces exactly what the continuity principle said. It's an alternative way of looking at the continuity principle. Why does water go less distant from the higher hole? Well, there's a couple things that come out of this experiment here. First off, if there is a lid on top of this, if this is completely sealed, then water is not going to come out of these pipes at all. And the reason it's not going to come out is gravity is going to pull down, and as gravity starts pulling down on those, pulling down, some of the water will originally seep out, but there would be a vacuum that is created at the top. So as the water starts pulling down, there's a vacuum at the top that is applying, that is resisting its expansion of the water, expansion of the lack of air in that chamber, and therefore the water will not flow. Take your finger, put your straw in a glass of water, put your finger over the top, lift it up. The water will drop a tiny bit out of there, but it will stay in the straw because the water, there's a pressure or an absence of air that's creating a negative pressure in that container. If this container has an open lid, then there is a greater potential energy or greater vertical drop of the water to the bottom hole. If there's a greater vertical drop to the water at the bottom hole, then you have a greater velocity coming out of that hole, greater potential energy to greater kinetic energy, and therefore the water with a greater kinetic energy has a greater initial horizontal velocity, so it travels further in the x direction. Projectile motion. Along these same lines, as this water is falling, this is a very interesting fact. You can try this at home. Go to your faucet and check out what happens to water as it falls out of a faucet in your sink. It's going to thin out to a certain point, at which point it starts to actually crisscross itself. If you look at a waterfall, it gets thinner and thinner and thinner as it falls. Why does that happen? Well, because the water is falling faster and faster and faster. As that water is falling faster and faster and faster, there is less pressure internally in that fluid. As the velocity goes up, the pressure has to go down, and therefore the atmospheric pressure is going to push in on that, creating a thinner stream to the point where the water eventually is going so fast that the water stops traveling in a stream and it starts to lose its flow, its Lamar flow, and it starts crisscrossing itself. I have an interesting video on this, which I'm going to also share with you. So applications to Bernoulli are that when fluids are flowing fast, there is less pressure. If you go and look at, for example, a commercial sprayer that you would attach to a hose for maybe like a fertilizer for your yard, you'll find that there's a container. Maybe you have a container like this, and there is a attachment on the top. You attach a hose to this, and there's a little pipe that comes down into the sprayed material. What's happening there is that as the water is flowing through the sprayer, there's a drop in pressure in this zone. They limit this down to a smaller cross-sectional area. That is going to lead to a low pressure, and the fluid material that's in the container will get pulled up and it'll get added to the water stream and shot out the front end. It's a way of sucking that out. That works in an engine of a car. They use this in the engine of a car in a couple places, and this also works in the in testing pressure, as you could see here in this picture, we have some pressure gauges, and all they have done here is they've created small holes, and so this water is flowing faster, so there's a lower pressure, so the gauge will feel that pressure and turn to a lower level. So the faster the water is moving, the lower the pressure it is going to experience. And these are called venturi tubes, which are nice little, which are a way of testing and experimenting with this. You have high pressure air flowing in on the left. You have it go through this restrained area, and you will see that this water level, which would naturally be level, rises up in this one area because there is a lower pressure in this tube, and it's sucking it up. There are other phenomena that we run into. The most common one is airflow around things like golf balls and wings. Here we have a golf ball. That golf ball, as it's moving, any ball, it doesn't have to be a golf ball, but that ball, as it's moving, is experiencing airflow. It's moving in this direction. It has to pass through the air, so the air is passing over it backwards. The air that's here has to go up and over and around the ball, which is creating a point where the air has to speed up. The air that's coming from here and here has to travel a greater distance than the air that's traveling straight. So you could see here, we've talked about this in early physics. That's displacement, that's distance. The air that has to go in a straight line is going to travel less distance than the air that has to go up and over the ball to get back into its stream. And so that air that has to go up and over has to pick up its speed, creating a low pressure. And so the ball, as it's spinning, has a low pressure all the way around it. This is how we get things like knuckleballs and curve balls in baseball, because there are on the ball stitching, and if we put that stitching in the right spot and we're throwing the ball fast enough, we can get it to do some really interesting things caused by Bernoulli's principle. We also can get the same thing to occur in an airplane wing. An airplane has 4 forces on it: lift and gravity. They are working against each other. And then forward thrust and air resistance. They are the horizontal forces acting against each other. To get lift, we must have the air flow over the wing. And so as you could see in this picture, some of the air is flowing up and over the wing, creating a faster flow rate. Now, this is, I think some of us have talked about this earlier, that we have experiences where we've seen other YouTube videos where they talk about this in a much more detailed calculus-based explanation. And this is a basic explanation of how this works. There are more detailed descriptions on this, so just keep that in mind. This is not, you can't go out and build an airplane based on what I'm about to say here, but this is a generality. There are exceptions. But ultimately, as a plane is moving down a runway caused by the engines thrusting it forward, the air has to go up and over the wing, and when it goes up and over the wing, it is going faster than the air below the wing, and therefore you create a low pressure. That low pressure on top and a high pressure, more importantly, on bottom, want to meet up to create equalization. And so the high pressure pushes up and the plane lifts. You slow down the plane, you slow down the air, you lower the amount of lift you have. And so this is the basic understanding of an airplane wing. If you have any questions, don't hesitate to ask me. I am going to share with you a couple other videos that contain some information, but this is Bernoulli's principle. Have a great day.